Hi again everyone, Dr. P here, and in this video we'll go ahead and take a look at using nitrogen nucleophiles to add to aldehydes and ketones, and that is going to give us formation of imines and enamines. So let's take a look at what these molecules are first of all. Let me just scoot some of my stuff around here. All right. So let's look at imine formation. In this case, we're going to have a primary amine as the nucleophile. So we will have our ketone or aldehyde, and then we will react that with this guy here, which is our primary amine. And we haven't talked about amine nomenclature and types of amines. We'll talk about that in chapter 24. But primary, secondary, tertiary for amines refers to how many carbon chains are attached. So it's a little different than for alcohols and alkyl halides. This is a reversible reaction, and it requires a little bit of acid. So in this case, a pH of around 5 is ideal. And the product we get is an imine, which has a carbon-nitrogen double bond. And this is our imine here. It's also known as a Schiff base, if I can spell it correctly. S-C-H-I-F-F, Schiff's base, or Schiff base. But the UPAC nomenclature would be imine, referring to the type of molecule. Now, why are we using pH 5? Well, there's a problem here. So remember when we looked at, I've got it right here. Let's say we looked at the acid-catalyzed formation of a hemiacetal. All right, so here's my hemiacetal. So it's kind of like that. Okay, so we protonate first to activate our carbonyl, and then our alcohol can add in. Well, analogously, we would protonate first, and our amine would add in. There's a couple of problems with that. One, we don't actually have to activate the carbonyl quite as much. We don't have to make it that much more reactive because nitrogen is a better nucleophile. Amines are better nucleophiles than alcohols. Second, amines are bases. So if we have H plus present, it's more likely to protonate the amine than it is to protonate the carbonyl there. So this is one of those kind of weird cases. So let's just say this. We'll say at pH approximately 5, we have both R double prime NH2 and R double prime, there should be a bond, I'll put a bond there, NH3 plus. So we have some unprotonated amine and some protonated, and this guy now can serve to be the proton donator, or help with the proton transfer. We will see another difference when I actually go ahead and show you guys the mechanism. And that other difference is that we'll actually have a negative charge present when we have acid present. I know last lecture I said don't do that. Well, this is the one exception, imine and enamine formation. All right, so if we have a primary amine as a nucleophile, we'll get an imine. If we have a secondary amine, we'll get an enamine. So secondary amine nucleophile. And we'll go ahead and take our same ketone here, and then we'll react it with R and so let's do double prime and triple prime, because really these guys could be, I'll put my lone pair in there, why not? These alkyl chains could be anything, so they don't have to be symmetric. Again, pH of around 5 is ideal. And then the product we get is actually a little bit different. So we'll have our RC, and you know, I need to redraw this. I do apologize. I realize I got a little ahead of myself there. RC double bond O CH2 R prime. That's what we need there. We need alpha, one or more alpha hydrogens. So remember, that's the alpha position. So what we end up getting now is double bond C H R prime, and here I've got my R double prime and my R 1, 2, 3 triple prime. Okay, so I've got all these alkyl chains here. I've got my ketone that has alpha hydrogens. What happens is I get a new double bond between the carbonyl carbon and the alpha carbon, so I lose one of those hydrogens. That's my new double bond there. And I get a new carbon-nitrogen single bond. And we'll look at why we get this type of structure with a CC double bond in the enamine. While we got a CN double bond in the imine. And once again, at pH 5, approximately, we have both R double prime N, R triple prime H, and R double prime N, R triple prime H, H with a positive charge. We've got both of those species. Okay? All right, so let's take a look at the mechanism of imine formation, and then we'll look at the mechanism of enamine formation. All right, so our first step is actually going to be nucleophilic attack. So we'll have R, C, double bond O, lone pair, R prime, and then R, double prime, N, H, H, lone pair. Okay, so this is where things are a little different. Remember, this is the exception and exception to no neg charges in acid. Okay, so this is these two imines and enamines are going to be exceptions to my rule of no negative charges in acid. Okay, so what does this give us now? This gives us now we have RCO with 3 lone pairs and a negative charge, R prime, and then here we have N, R double prime, H, H with positive charge. Okay, the next step is some proton transfers. So I'll have another molecule of R NH2 here, or sorry, R double prime NH2. And that will pull off a proton from our protonated nitrogen here. Those electrons go back onto that nitrogen. I'll also have a molecule, because remember, I have both these species present. I have my R double prime NH3 plus. So I have both of these species present. So let's go ahead and draw this guy here. R double prime, positive charge there. So now I can protonate my oxygen there. Okay, so now what does that give me? That gives me now R, C, R prime. I've got oxygen, hydrogen, my lone pairs down here. I've got a nitrogen, I've got my R double prime, and I have one hydrogen and a lone pair. Now we can get additional protonation. So if I have another molecule of the protonated amine here, I'll do another protonation. So this should, this is starting to look a little bit like acetal formation, right? Because I have my my leaving group now. Now I can lose that leaving group, and so the lone pair on the nitrogen will come and form a carbon-nitrogen double bond, and that will kick off the OH leaving group there. And then that will leave me with R, C, R prime, double bond N, R double prime, H, positive charge. And then another molecule of my double prime, of my amine can come along and deprotonate there. And I'll get my final product here, R, C, R prime, double bond N, R double prime with the lone pair. And there's my imine. There we go. So some things that you want to make sure you do here is you want to keep track of your proton transfers. And in particular, no negative charges on nitrogen. Okay, so I don't want to see anything like no, nothing like that. Okay, no negative charges on nitrogen. This is the only negative charge you get to have, the one on that oxygen there in the first step. Okay, after that it's all positive charges. Now, there's a bunch of different proton transfers going on here. We refer to this one as solvent-mediated proton transfer. So I'll just write that here, solvent-mediated proton transfer. If you want to save space, we have, it's okay to do it the following way. So instead of solvent-mediated can do direct proton transfer. So if I had that structure, instead of drawing those additional excuse me, molecules of solvent, or in this case the amine, I could just draw the oxygen pulling a proton off of the nitrogen that has, sorry, this guy had a positive charge there. So instead of having one molecule of amine pull off a proton there and have another molecule of protonated amine give up a proton to the oxygen, you could, I will allow this, you could have your oxygen, a lone pair from the oxygen, grab a hydrogen, a proton, from the nitrogen on the other part of the molecule there. It probably actually happens this way, but I'm okay with you drawing it in the direct proton transfer because it's a little quicker to draw. Okay, so we'll just say here, Dr. P is okay drawing it this way. It's quicker. Smiley face. All right. So that's our imine formation. So again, we have our nucleophilic attack, proton transfer, either with our solvent-mediated or our direct proton transfer. Either one of these gives us this next intermediate, which then we get another proton transfer, then leaving group leaving, and our final proton transfer to get our imine. Now the enamine is similar, only our final proton transfer is going to be a little bit different. So let's go ahead and take a look at that. All right, so let's take a look at this here. So we will start with our R, C, double bond O, C, H2, R prime. And now I'll have my R double prime N, R triple prime, H. The first step is the same. We have nucleophilic attack on the carbonyl carbon by the amine nitrogen. And that now gives us R, C, CH2, R prime, N, H, R triple prime, R double prime, O minus. And we'll go ahead now and have our proton transfers, which I'm going to draw out, but again, if you want to, you can do the direct proton transfer. I forgot to put the positive charge there. And then up here, I've got H, N, H, R, double prime, R, triple prime, positive charge. And that negative charge pulls that guy off. So now we get R, C, O, H, CH2, R prime, N, lone pair, R double prime, R triple prime. All right. Now we'll have another proton transfer. So again, it's the same so far as the imine formation. So here's our positively charged protonated species there that gives up a proton picked up by the oxygen lone pair there, and now we get to RC, C, double bond, oops, I'm sorry, RC, single bond O, H, H, lone pair, positive charge, and CH2R prime. And then here we have N, lone pair, R triple prime, R double prime. And now we will have loss of leaving group. And again, it's the driving force of the electrons on the nitrogen that are going to help kick off the water, the H2O leaving group. And that gives us now R, C, double bond N, R, double prime, R, triple prime, positive charge there, C, H, H, R prime. So now I'm drawing this out because our last proton transfers, this is different. Remember before we had a proton on the nitrogen that could be pulled off, and now we've got a carbon-nitrogen double bond. Well, here we've got our carbon-nitrogen double bond, but a positive charge on the carbon. So our final proton transfer is actually going to be one of the alpha protons here. So we'll pull off that proton. Those electrons will go down to form a new carbon-carbon double bond, and then the electrons in the carbon-nitrogen double bond, one pair of those, is going to go up onto the nitrogen. And that's going to give us now RC, double bond C, H, R prime, N, R double prime, R triple prime, and a lone pair. And that is our enamine. There we go. And again, like previously, like imine mechanism can do direct proton transfer. Transfer here. So again, in this step, we can do the direct proton transfer. So like this one, if we wanted to. All right. So this gives us our enamine, and it's called an enamine because it's an amine and an alkene. So enamine. In a couple chapters, we'll see enols, which are alkenes and alcohols, enols, enamines. So a slightly different little functional group involving nitrogen here. Now these reactions are reversible, and I think in the in-class meeting we'll look at how to draw the reverse mechanisms of these reactions. But again, it's the same essential thing for both enamine and imine formation. We have nucleophilic attack, proton transfer to make a neutral species, additional proton transfer to make a good leaving group. Leaving group leaves, and then we get deprotonation of the nitrogen in the imine, or to make the imine. In the enamine, because we don't have any protons on the nitrogen, it's one of the alpha protons that gets pulled off, and we get the enamine when it's all said and done. In both cases, we want to keep track of our proton transfers and no negative charges on nitrogen. Stuff like that is bad. All right. So you want to be able to do these mechanisms. I will ask you to draw these types of mechanisms on the quiz and exam. All right. So that's about it for the nitrogen nucleophiles, formation of imines and enamines from ketones. In the next lecture video, I think we'll look at some other carbon nucleophiles, adding to aldehydes and ketones. We've already seen things like the Grignard, but we'll look at a different reaction next time called the Wittig. I always thought it was kind of a nifty reaction. And anyway, we'll talk more about that next time. All right. Well, until then, stay safe out there. Bye now.